Balancing equations using half reactions. You've been balancing equations since Science 10 and no doubt have your own technique that works well for you. But this technique is based on observation and only works if all the components of the reaction are present in the equation. In what follows, you'll be asked to write a balanced net ionic equation after being given only a partial equation reacting in an acidic solution. We call these skeleton equations. The process involved in balancing net ionic equations are broken down into steps. We will follow fairly closely to the steps outlined in your text. Rather than simply writing out all the steps, we will simultaneously work through this problem incorporating the steps as we go. So we're asked to write out a net ionic equation, and by implication a balanced equation, for the reaction of a bromate ion with sulfur dioxide, which will form bromine and a sulfate ion. The first step is to write out the half reactions. Some, if not all, of the components of this reaction may not be in your data book, so we compose our own half reactions. Step 1. Write an unbalanced half-reaction equation by incorporating only the substance undergoing oxidation and another half-reaction equation incorporating only the substance undergoing reduction. It seems like a big step, but what we're only focusing on are the two atoms undergoing the redox reaction. It's not important which is being oxidized or reduced at this stage, but we can usually discount oxygen and hydrogen when we have two other different atoms in the equation. So in writing out the half reactions, we only use the atom or the compounds to which the atom is connected, and ignore any hydrogen and or oxygen compounds. These are not only unbalanced, but the upper equation is missing oxygen atoms on the product side, but we'll deal with this later. In step 2, we balance atoms other than hydrogen and oxygen. A coefficient of 2 balances up the bromine atoms. The sulfur atoms are already balanced. Water molecules are added to the side of the equation deficient in oxygen. We add enough water molecules to balance out the oxygen atoms. In the upper equation, there are a total of 6 oxygen atoms on the reactant side. This is why it was important to balance the non-hydrogen, non-oxygen atoms first. That coefficient of 2 gives us 6 oxygen atoms in total. To balance the 6 oxygen atoms, 6 water molecules are added. The lower equation has 2 atoms of oxygen on the reactant side and 4 on the product side. So we add 2 water molecules to the reactant side. Step 4. Balance hydrogen atoms by adding hydrogen ions. For the upper equation, the 12 hydrogen atoms belonging to the water on the product side are balanced by adding 12 hydrogen ions on the reactant side. And similarly, the 4 hydrogen atoms of the lower equation are also balanced with hydrogen ions. Step 5. Balance charges by adding electrons to the more positive side. To ensure that the number of electrons lost in the oxidation reaction equals the number of electrons gained in the reduction reaction, we make sure that the total charge on both sides of the equation is the same by adding electrons. The reactant side of the upper equation shows a net charge of a positive 10. That is, the 12 positive ions minus the 2 negative ions. The product side has a net charge of 0. So the side we need to add electrons on to equalize the charge is the more positive, in this case the reactant side. Likewise, the lower reaction has a greater positive charge on the product side and so is equalized with electrons. A redox equation ensures that we see the number of electrons lost equals the number of electrons gained. We achieve this by multiplying the lower equation by a factor of 5, making the number of electrons on both sides equal to 10. Once the electrons are balanced, we're now free to finally combine the two half reactions. Adding the two equations together shows some redundancy. There are 12 hydrogen ions on the reactant side and 20 on the product side, and 10 waters on the reactant side and 6 waters on the product side. Some reduction of compounds appearing on both sides of the equation needs to occur. The 10 waters on the reactant side eliminate 6 waters on the product side, leaving a balance on the reactant side of 4 water molecules. The hydrogen ions are taken care of in the same way. Here, the final equation is shown in its net form. Now, your textbook goes on to discuss balancing chemical equations using half reactions in basic solutions. You will not be assessed on this material.